And hello, everyone. It's my pleasure to present my work here. And thanks very much for Professor Li Dak's invitation. Today, my topic is a nonlinear analysis of current outputs for piezoelectric energy harvesting. I'm from Shandong University, Weihai, China. And now I'm an associate professor in School of Mechanical and Electrical and Information Engineering. This is outline of my presentation, and I will talk about why we modeling this current output nonlinearity, and how we model it and how we use it, and then we can give our conclusion. And first, we start from the research background and why we use the energy harvesting. And this is the first microchip, first single chip computer processor issued by Intel in 1971. And we can calculate its current or its power consumption by the product of voltage and current. And this is now the microchip MCU. We can also calculate its energy consumption. We can see actually it's highly reduced energy consumption. However, its clock rate is greatly increased. So that means we can calculate much faster, but with less energy. And what about the energy harvesting trend nowadays? And we can see that we take the solar cell as an example. This is the photovoltaic transfer efficiency during the last few decades. We can see that now it's nearly 47% of transfer efficiency for the solar energy. But I can't find the precise quantified piezoelectric energy harvesting data, but we find a lot of papers that studying ferroelectric material that's enhance the energy harvesting. They can transfer more energy from vibration to electricity. And we can find a lot of paper studying about interface circuits, and they propose a lot of interface circuit that extracts much energy from the ferroelectric materials. And also, nowadays we have a lot of power management module that are very powerful with less energy consumption but efficient, a large efficiency. And we also found there are lots of energy storage materials such as capacitors and the second battery that can preserve the electricity with less loss. So we can see that actually we can convert more energy from the vibration. Yeah. So with less energy consumption and more energy harvesting from the much more energy harvested from the ambient environments, there would be a balance that is self-powered. So that's our goal for the energy harvesting. And for an energy harvesting system that we can convert the ambient and vibrations such as the cargoes and the industrial and the trains by using the piezo elements to transfer the vibration to electricity. And then we use the interface circuit. Why we use the interface circuit? Because the piezoelectrics, their electrical property is very different. They have very large resistance and is in parallel with a capacitor. So usually we use oscillating circuit to extract this energy from the capacitor to this circuit, and then we use a power management module to modulate this energy, and in the end, used in the end applications. For this piezoelectric energy harvesting system, they are mainly designed for low voltage device or module. I would say that's less than 5 milliwatt. That's watt, and so that's for MEMS and low energy consumption sensors. It's not for the bubble for the computer. I think it's for low energy consumption devices. And another, I think, is in this energy harvesting system, we need a very good energy storage device such as thin film batteries, supercapacitors. And also we will need a power management module is needed in this energy harvesting system. For the installation of the PEH, there are mainly two types. One is we take the piezo patch on the base structure, so this piezoelectric ceramic can deform or vibrate with the base structure. And another is we can put the piezo patch on a cantilever beam, and this cantilever beam will amplify this base movement, so we can generate more energy. However, sometimes we want to a large deformation or very large displacement. However, this is not always good for the energy harvesting, because with a large deformation, the nonlinearity occurs. This is the constitutive equation for the direct piezoelectricity. This is always correct for this equation. However, this D, that is the piezoelectric coefficient, is nonlinear actually. According to Butcher's research, and we can see when with the large mechanical stress, the polarization will decrease. According to this, it will lead to the D33 decrease. Even we take away, release this mechanical stress, and the D33 will have a decrease on this value. It can't come back to the original value. And we can say that the harvest energy from the piezoelectric ceramics is proportional to the dt square. That means if the D33 decreases, actually we harvest even is in a very large mechanical stress, and we don't harvest more energy. And I have analyzed piezo ceramic attached to a cantilever beam, and when this cantilever beam is vibrates in 1g acceleration, and at about 40 hertz, we can see there is a small nonlinearity in the current output. And there is also a study about the PE model and the PT model. The PT model is the mechanical stress induced polarization, and the PE model is the electrical field induced polarization. And Professor Guillermo Daniel has already made this scaling law between these two models. So in my study, first we studied from the piezoceramics. And for example, this is piezoceramic, as it depots are randomly arranged in the wall. And when it is subjected to a high electric field, and this is the polarized state. And then if we apply a low stress on this ceramic, and it will generate electric charges. But if we apply a very high stress on this piezoelectric ceramics, and it will depolarize this piezoceramics. And for this polarized and the piezoelectric, direct piezoelectricity, we have modeled this whole hysteresis loop with the hysteresis model. And to get this its parameters, we make the deconvolution of the first polarization curve. That we got a spectrum. The first polarization curve is this curve, and that means we apply a very high electric field to piezoceramic, and we get this model. Usually, that model is a very static model. Usually, we are applying the dynamic electric field to this piezoceramic. To take the dynamic contribution, we usually use a derivative contribution here. However, when the frequency gets higher, and this integral derivative always overestimate this loop area, and so it's not suitable for dynamic contribution. So we are thinking of using a fractional derivative to this model, and it works very good. And after modeling this piezoceramic electric model, we using the scaling law E equals FTP to model this mechanical excitation. And that means this XX is the mechanical stress, and this y-axis is the polarization. Polarization can be get from the integration of currents with time. So that means we can accurately predict or calculate this polarization. That means we can calculate the currents of this piezoceramic under different frequency and different amplitude of the mechanical stress. And by using this model, the mechanical excitation and the electrical excitation model, we propose Aerosol cycle technique. That's how it works. First, we apply a constant electric field to this piezoceramic, and then we keep the electric field constant, and we apply a mechanical stress to that. And we keep the mechanical stress constant, and we decrease the electric field, and then we decrease the mechanical stress. Okay, in a loop, in this direction, that means we are harvesting energy, and this loop area means represents the energy we harvest. And when we use this model, actually we use Watt amplifier to provide electric field. That is, we are imparting energy to this energy harvesting system. How we can see we are harvesting energy? We can see this curve, and in this gray part, that means the the energy we impose to this system. And this blue area means the energy we harvest. Once this area is larger than this one, that means we are harvesting energy. Does it mean Aerosol cycle techniques always harvesting energy? No, it doesn't. We have make a lot of simulations and experiments. We found that if we have small mechanical stress, we harvest less energy. But if we use a larger electric field, here you can see there the cross area here. This cross area means we are losing energy. So once we use Aerosol cycle technique, we have to carefully couple the electric field and with the mechanical stress. If not, sometimes we are losing energy. And the above model sometimes is very complicated, and in these days I'm looking for a much simpler way to modeling this current output of piezoceramic. That is our measuring bench. Here, this part is the piezo stack actuator, and this gray one is our piezoceramic bank. And here we have a force sensor to measure the force we apply to this piezoceramic, and we use this screw to give a preload of this piezoceramic. And we use a standard circuit to first we find the optimal load for this system, and then we apply the different frequency and different preload to this piezoceramic, and we take 80 hertz excitation as an example. When this preload is higher, and we get more energy, but when it gets higher, we can the harvest energy is decreasing. Actually, this is the output power. Output power is decreasing, then it's increasing, and finally it's decreasing. And that means it's not always increasing as the preload of the mechanical stress. That is a relatively hard PZT. And for a very soft PZT, sometimes we can't find this double peak. Here, we call this phenomenon as double peak. As far as I see, I think it's the nonlinearity of the D33 causes this the double peak phenomenon. And we use curve fitting to get an empirical equation considering the preload frequency stress variation to get this current output model. And it's very it's relatively very accurate to predict the current output. We make this experiment under uniform stress distribution, because this is a back PZT, and the applied force is uniform. How about on a cantilever beam? That is we can use a finite element analysis to simulate or to calculate this stress distribution on each part of this piezoceramic, and we consider each part as a current source. So we make the sum of these different current source, so we can get a total current output. And we compared our experiment with with our simulation. We found that it's fits well with each other. That means the empirical equation is relatively precise, yeah, accurately. And then we are doing some more research on the modeling of current output for buck PZT, and we consider the frequency and the stress amplitude and preload and D33 nonlinearity and PZT geometry. And we use the electromechanical grouping function accompanied with energy conservation and piezoelectric functions, and also the force vectors. Now we got our new current output model, and we will publish this. We are looking forward. We're looking forward to publish it sooner. Okay, and for the optimization for the pH in the future, I think we should carefully consider the grouping between the piezoelectric elements with the interface circuit, because this this interface circuit will affect a lot of the PZT current output, because it will affect the vibration and the electric field on this PZT. So if we want to develop a very efficient interface circuit, we have to consider its grouping. And we are also doing some circuit design for our Aerosol cycle technique. We take the SSHI theoretical waveform example. We can see that with the voltage reverse, and we can get a very higher voltage. If we reverse much more times, maybe we can get a higher voltage that can act as a Aerosol cycle electric field, so that we can make this Aerosol cycle technique self-powered. And the next, we are also doing some research on this self-powered interface circuit, because right now we are imposing energy to this system that's not always suitable for the installation in the real environment. So we want to use this self-powered Aerosol cycle technique for our next future study. Yeah. We are also doing some experiments for the self-powered wireless sensor nodes, and we use LTC3588 as a power management module, and we use two resistance to simulate this MCU and RF to its sleep mode and work mode by switch on, switch off this switch, and up to our simulation, now we can get that. Now it's totally self-powered with 100 seconds sleeping mode and 50 milliseconds work mode. And in the future, I think we will do to make a proper prototype for this self-powered wireless sensor networks. Okay, so here comes our conclusion. And that's our fractional derivative factor is effective to compensate for the nonlinearity of the wall movement and also for the nonlinearity of the current output. And the depolarization should be carefully considered both in the soft PZT and hard PZT. As we have said, we can see the double peak phenomenon in the energy harvesting system. So it's necessary to monitor or calculate this stress distribution on of the piezo ceramic. Otherwise, the mechanical stress will depolarize this piezo ceramic. So we can use make the most of PEH considering the double peak of output to make the PZT work on its proper mode. And a self-powered wireless sensor node can be realized by the efficient power management. We can adjust or change the sleeping mode to make the wireless sensor node totally self-powered. And for the interface circuit design, it's very important in piezoelectric energy harvesting because of its electrical property, we have usually, generally speaking, the electricity density of the piezo ceramic is relatively high. However, it's difficult to extract the electric charge from the piezo ceramic because of its high resistance and small capacitance. So when we use interface circuits, we should carefully consider this electromechanical coupling so that we can get a better interface circuit. Yeah. And I want to say thanks for your listening, and thanks to my co-authors, my master students, and the Professor Lida giving me the chance to talk on the energy harvesting dialogue. And thanks for the financial support from SFC and the Shandong University. Okay, thanks for listening, and I'm waiting for your questions.
Thank you very much for this presentation, nice presentation. I'm just waiting for any questions. So I'm checking also the chat. So there is no question on the chat. So let me ask first question because
okay.
I thought about the source of excitation in your system. For example, because you tested in the laboratory the system which you invented. So the problem is that in this, for example, in this system, you control the stress. So this is no resonator. In fact, you discussed resonator as a beam in some other part of a lecture, but probably this is still under preparation because I cannot see this beam here. And the second aspect is related to the also to the source, because in this ambient application, ambient source application, we expect that we have some variability of source, for example, variability of frequency and variability of amplitude. So could you answer these two questions? First, about that you control the the stress. In fact, there is no resonator. And the second, how you test variability of a source, because I see that you rather test very harmonic signal. Yeah.
Yeah.
Could you comment on that? Yeah.
Yeah, the first question is about the stress. Actually,
I think that this is in the laboratory you can do this, but
yeah,
you also discussed the beam. So have you tested the beam configuration in the laboratory?
the beam. Actually, we are doing some broadband energy harvesting with how to say with two beams or three beams together, and we didn't. Now we are testing the current output of this. No, it's not current output. It's the voltage of the beam. But at first, I would like to say that in our real in the environment, usually I study in the first case that's this piezoceramic will vibrate or deform with the space structure. So piezoceramic under a railway or under the road. So actually, it's already have a preload, yes, on the piezoceramic. So in my opinion, we have to consider this preload stress on this piezoceramic, and in the
what about the variability of the source? Yeah. What about this variability? Yeah.
Yeah, we didn't. We usually we take just for one frequency, and we didn't test a lot a different frequency, the frequency variation in energy harvesting, because for the circuit design, it's usually not it's not very simple. But let me show you this circuit. Yeah, this. Oh, sorry.
Okay.
This circuit is the this part. This part is the peak detection of this of the voltage. Sometimes it can act as a switch, or it will change according to the frequency, but it's not so sensitive. Sometimes for the small peak, it will ignore this small peak. But yeah, as you said, this different frequency is usually very difficult for us to harvest. And in the future work, I think I will study the different frequency energy harvesting, especially on the circuit design. Yeah.
Okay, and one more question is about you discussed nonlinearity with some map, three-dimensional map. There was a map, and you told that there is some effect of no, this was here.
Yeah.
But I would like to comment because sometimes it is useful to look for some frequency sweep if you increase frequency and if you decrease frequency, and then if you have some discrepancy between increasing and decreasing path, then you can tell that this is a kind of dynamic hysteresis, and this is caused by nonlinearity. So this is my only my comment. Yeah. I just want to advise you that maybe you can also try to calculate some frequency sweep. Up and down. Yeah. So So thank you. Thank you. Very, very nice presentation. Maybe there are some other questions, yeah, from the audience, yeah. There is one from the chat, yeah.
Yeah. Okay. Professor Chris Bowen and yeah, I see. Let me. This is it's about 5 mega watts per meter. I think it's yeah 500 watts per millimeter. Yeah, it's relative. Yeah, it's relative a high amplitude of the electric field. However, we have some experiments on 50 volts per millimeter, and also we can get good result. I think for the applied for the applied for the applied electric fields, for 50 to 500 watts per millimeter is useful in Aerosol cycle technique. If with a higher with a higher electric field, maybe some piezoceramic will have a small depolarization on it. Yeah. Yeah. Oh.
Yeah, there is a question about some.
Thanks, Chris.
Okay. Yeah. So, any other questions from audience? Yeah, I think that the problem there is one problem which you probably because you need to have two sources. One source is variable stress or some vibration, and the second source is that you have also a variable electrical field. So the electrical field is the external electrical field in your yeah. So
that's
so then it is very special case because you have to combine these two effects and you analyze. So do you assume that you have the same frequency in mechanical source and electrical source? Is it the same frequency? Yeah.
Now, if we want to use this Aerosol cycle technique, we have to synchronize this this electric field according to the mechanical stress, because this is the from the atmosphere. Yeah. So it's very difficult in real in the yeah.
Okay, because this is combined with switching. Yeah, you switch.
Okay. We are trying to find a solution for this, and yeah, it's really difficult, but we want to solve it. Yeah.
Okay, because I was thinking that maybe you can design your resonator in some way that you have a variable charge or variable electrical field. Yeah. So this is important to propose maybe some realistic system. Yeah, for future. Yeah. And I think that this is because this is like a concept, and one should find some realistic example. For example, I was thinking about some kind of resonator which could also have some electrical field involved. So this is possible. However, it is difficult to maybe to find the special such a special case. Yeah. Okay.
Yeah.
So maybe some other questions. If there are no questions, so let me thank you once again. A very nice presentation. So thank you very much for presenting these results, and this this presentation is also recorded. So if somebody wants to look inside later, so it would be on our webpage, Dialog web page, and I would like also to thank all the participants to come to our seminar and to participate, and we hope that some of the participants can present some results in the next weeks. So for the next week, we actually have the speaker. We already have the speaker. So this would be Professor Carlo Trigona from Catania University, and however, we hope that maybe there are some other concepts, materials, or maybe some power electronics concepts for energy harvesting or dynamics. So involved concepts, and please send us the title of this presentation, and we can schedule your presentation into the next week's so meetings. So this would be our continuation of seminars. Yeah, okay. Okay.
Thanks, Professor Lidak. Yeah.
Thank you to all the participants. Yeah, and especially to Zhang for presenting.